and well, what we get is a function of energy in the angle. Let me write down this function. So before I write it, let's just check, do a zeroth order check that we haven't made a mistake. So the zeroth order check is that this should be dimensionless. So let us see. So this is dimension, and immediately we see that there is something wrong. So because I forgot that there is a power of 4 here. So with that amendment, this works. So this has 4 momenta, and this has 4 momenta. So denominator here is very simple, right? So this is the total energy in the center of mass, P plus P prime. So which you can also say from the explicit expressions. So this denominator is simply 4e raised to the 4th power. Okay? And so each of these guys here in the brackets will produce e to the 4 times maybe some angles. Because this will be products of momenta that are all proportional to p. And well, some terms will contain also the mass of the muon. So if one collects all these terms, so there will be a 1 here, mu squared divided by e squared. Plus 1 minus m mu squared divided by e squared times the cosine squared of theta. So, right. So this is just the result of the calculation. And then we just substitute this into the formula for the cross section. So the differential cross section will be equal to the amplitude square then we should divide by, so in the numerator what we have is the relative velocity times masses of the particles. So let me write it like that, but this is nothing but 4e e plus, e minus times the relative velocity. And that's equal to 4 times square root of k times p prime squared minus m electron squared m electron plus m electron minus squared. So there was this formula in the expression for the cross section. You see that we neglected the masses of electrons compared to their momenta, so what we get is just 4 times the scalar product of momenta. Okay, so then p prime dot is equal to twice the energy squared d phi was calculated in the last lecture. So this is the two particle phase volume. So the phase volume was equal to the element of the solid angle in which the muon flies, divided by 32 pi squared, and the square root of 1 minus m mu squared divided by e squared. So finally, we have all the ingredients. Out of which we can get the differential cross-section. So that's it. This is the final answer, right? We just multiplied the amplitude squared by the phase space and divided by the center of mass energy squared. So indeed, it has the predicted form. So it at very large energies, you see that then all of these terms with the mass of the muon go away. And so we have some coefficient that depends on the angle, by the way, multiplying alpha squared and divided by the energy squared. Near threshold, so this bracket becomes a constant. So when we set e to m, so this term goes to 0, which also could be anticipated. Because, okay, so at threshold, muons are produced at rest. So they don't fly anywhere. Therefore, the cross-section should not depend on the direction where they fly, right? Because they just sit at one point. And indeed, we see that this happens because of the cancellation between 1 and this term. And so at the end, everything is, the cross-section is determined by the square root that comes from the phase space. So this is the final answer. One can integrate it over the angles to obtain the total cross-section. So this is the final result of the calculation. And it describes a curve of this shape. So this formula describes also the angular distribution, which, well, you see that it depends on the angle like that. So it has a minimum at pi over 2, and then this, well, the same at pi. So it is, so muons will tend to be produced in the, more muons will be produced in the forward directions than in the perpendicular direction. So the perpendicular direction, the count of the number of produced muons will be the smallest, but still this curve doesn't go all the way to 0, so there is a non-zero probability to produce a muon that would fly in the out of the plane, out of the reaction. So okay, it took us like more than an hour to do this calculation. And believe me, preparing this was even more, with all the coefficients and traces, etc., etc. And this is the simplest QED calculation. So quantum field theory is not, I mean, it's takes a little bit of time and effort to do calculations. And so, well, this was the simplest example. Now, since I have another 20 minutes, I'll just summarize the course. I guess that would be probably useful if I say some general words about what I covered in the lectures. So quantum field theory is all about particles. So the basic objects there, and about quantum mechanics. So the basic operators create and annihilate particles. And so we have operators A and A dagger. That create particles with momenta p and k. So this can be a commutator or an anti-commutator, depending on if these particles are bosons or fermions. And so the Hilbert space of these particles is the Fock space, where generic state contains particles with various momenta. So there's we start with an empty state, and then we can add some number of particles. So as we saw, this picture is useful in condensed matter theory or in many body physics, where we are dealing with the systems where the number of particles is big. And then it is convenient to introduce also a Fourier transform of this particle creation and annihilation operators, which are field operators. So they are operator-valued functions in space-time. And using that formalism, one can describe, say, Bose-Einstein condensation and things like that, superconductivity. So it's a useful way to understand the collective behavior of many numbers, big numbers of particles. However, the main theme of our course was relativistic field theory. And a completely new feature of relativistic fields is that the number of particles is actually not conserved. I don't know if you noticed that at which point we started to deal with the situations where we have processes in which the number of particles, particles could be created in pairs, and they can annihilate. And so this is a feature of relativistic field theory. It's just a generic feature. All particle interactions can be understood as processes of creation and annihilation of virtual particles. And even the forces acting between particles, like the electromagnetic interactions, can be understood as the results of exchange of photons between electrons. And so this is actually a general principle that underlies all interactions in nature. They all can be understood as exchanges of various virtual particles. So forces are equivalent to exchange of to the process of creation of a particle that is then absorbed by another current, and so this leads to interaction, say, between electromagnetic currents. Then the formalism of quantum field theory is based on, well, usual Lagrangian Hamiltonian mechanics, but applied to systems with infinite number of degrees of freedom. So the starting point of all our analysis for a Lagrangian so the action of the form that had a form of an integral over space-time of some Lagrangian density that might have depended on fields and their derivatives. It is important to understand that we should treat this really as a mechanical system. So there is, in terms of, we are not inventing any new laws by considering fields. So we apply just the same laws of classical mechanics, classical Hamiltonian mechanics, and then quantum mechanics to quantize the fields, as we would do for any system with such and such number of degrees of freedom. So we just say that phi I of x and t, which we can write by phi I x of t. So x here is just a label, an index that parameterizes the degrees of freedom. So these are our basic dynamical variables. And we treat them as such so that we derive the equations of motion as we would do for any Lagrangian system. So we take a variation of the action and demand that this variation be zero on the equations of motion. So for this type of Lagrangians, the equations of motion then are written in this form. So we have studied quite a few cases where all the equations that we obtained were the equations that you already new, like the Maxwell's equations, or the Klein-Gordon equation and the Dirac equation. So in all the cases, we start with the Lagrangian. The equations of motion are just derived from its variation. An important feature of the Lagrangian mechanics, and in particular field theory, is that the relationship between symmetries and conservation laws. So in classical mechanics, this is not always emphasized. So sometimes in courses in mechanics, Noether theorem is also studied, but not always. The reason that in field theory it plays so prominent role is that applications of field theory in particle physics are so much based on symmetry. So the symmetry principles were extremely powerful during the history of physics in the last century. So all basic theories of fundamental interactions are based on symmetry. So the theory of relativity is, Einstein's theory of gravitation is based on general covariance. Electrodynamics, as we saw, follows completely from the requirement that the wave function of the electron is an unobservable quantity. All other modern theories of fundamental interactions are based on symmetry principles, which is generalization of this phase invariance in electrodynamics. So that's why symmetries are important. And once we have a symmetry, Noether theorem tells us how to derive a conserved current from the Lagrangian. So there is a Noether theorem that tells us that if the Lagrangian is invariant under transformations of coordinates of this form and accompanied by transformations of fields of this form, then the current will be, there will be conserved currents which are obtained in a uniform way from the Lagrangian. So Noether theorem tells us that this current is conserved. And then we studied several examples of field theories. So we studied the Klein-Gordon field. whose Lagrangian is this one. And we realized that it describes scalar particles of mass m by quantizing it using the usual. So here we went through through this whole procedure step by step, starting with the action. Then from the action you can get the Lagrangian. From the Lagrangian you get Hamiltonian and canonical variables. Then you replace Poisson brackets by commutators, and then you diagonalize the Hamiltonian. And this is the way how we saw that particles arise from just from expanding phi in the Fourier modes. For the Dirac field, we just use the shortcut way of arriving at the same picture. But in principle, one can do it step by step in the same way. So this describes charged fermions with mass m and spin 1/2. So in particular, this Lagrangian describes free electrons and positrons. And then we studied electromagnetic field and also interactions of it with the positrons and the electrons. So the Lagrangian that we wrote was this one. And so the way to arrive at this Lagrangian is first to realize that if you want to have a symmetry of the wave function with respect to phase rotations that are independent at each point, we need to introduce a compensating field. So that enters in the covariant derivative. So d mu is d mu minus I e a mu. And so A here appears as a compensating field that transforms in the opposite way to fermions. And so it gauges away the non-local, the derivative term in the transformation of the Lagrangian. But it has to be a dynamical field, so we have to write some Lagrangian for it. And in fact, this is the only Lagrangian that you can write that would contain two derivatives. It might not be immediately clear, but if you think a little bit about it, you will see that there are no other possibilities. And then we arrive at the Lagrangian of electrodynamics that describes Maxwell's equations. So the variation with respect to A would produce the Maxwell's equations. But now this field theory is interacting. So this is an example of an interacting field theory. Because it contains a term, so interaction term here is minus E a mu psi bar gamma mu psi. So you see that it contains three types of fields, and it describes the process of emission of a photon say by electron, or if you turn it around, this would describe annihilation of an electron-positron pair into a photon. Or if you turn it again around, that would be a production process of an electron-positron pair by a photon. And then we formulated rules how to calculate probabilities and how to calculate amplitudes of probabilities, treating this as a small perturbation, but in principle to arbitrary ordering. So Feynman diagrams allow one to compute corrections to an arbitrary order in perturbation theory. Well, we explicitly calculated only the simplest case where the diagram was of the leading order and it didn't contain loops. So the feature of this calculation, a feature of this calculation was that all the momenta were determined by conservation laws, right? So we didn't integrate over. So in principle, in the Feynman rules that we formulated, there are lots and lots of integrals over intermediate momenta of some particles in the diagram. In all the examples that we considered, these integrals are eliminated by delta function of momentum conservation. Now, if you consider loop diagrams, namely diagrams that contain closed contours, so now I'm talking about what you'll hear later in other courses in quantum field theory. So if you consider diagrams, say if you want to consider corrections to E plus or minus annihilation to muons, so one of the diagrams that you will get will have a loop of electrons renormalizing the photon propagator. So it turns out that this diagram is actually infinite. It diverges. Which has to be compensated by saying that the electric charge that stands in the Lagrangian is also infinite. So it can be compensated by renormalization of electric charge. So alpha, in fact, so there are two interesting effects. So first effect is that we have to renormalize the charge. So we need to assume that alpha that stands in the Lagrangian is not 1/37, but is some quantity that is infinite and compensates infinities that arise in diagrams. The second effect is that the renormalized charge will depend on the energy scale. So it will be to the leading order, it will be equal to alpha, but then there will be a correction of this form. So there will be some constant, which I don't remember, times the logarithm of the energy scale. Where mu is some arbitrary normalization. Well, these corrections of this type, they change a little. One effect of them is that they change the dimensional analysis that we did for field theories. so that couplings and masses that appear, parameters that appear in the Lagrangian, they gain anomalous dimensions. So their dimension starts to depend on the interaction strength. And so interactions that were marginal, like QED interaction is marginal, described by massless, by dimensionless coupling, which is independent of energy scale. In fact, due to quantum corrections, does obtain some dependence on energy, which is very slow, because this is just a logarithm and is multiplied by a small coupling. But it has important effects. It shows that at high energies or short distances, the QED interactions become stronger. And in particular, so they cannot be continued to arbitrary high energy because this function hits a pole. This is called the Landau pole. And so QED cannot be valid at any arbitrary energy scale. So this is a feature of almost any quantum field theory. There are some exceptions, but in many field theories that we do use in particle physics, cannot be extended to arbitrary high energies because the divergences render coupling constants non-perturbative at the energy scale. So you see, from this formula, what you conclude is that QED becomes non-perturbative at very high energy scale. Now, if you estimate what these energy scales are, this would be 10 to the, 100 GeV. So it is so high energy that it's not reachable in the experiment. But anyway, just formally, QED is not really a fully self-consistent theory. Okay, so then I guess this is not the only useful theory in particle physics. And theories that describe all interactions as we know them are based on a simple generalization of QED. So these are called non-abelian gauge theories. And so the Lagrangian looks exactly as the QED Lagrangian, but you have to understand letters in a different way. So psi in non-abelian gauge theories carries an extra index. Let's call it the color index. So it is a spinor, but it also has some labels that we call colors, which say run from, 1 to 3, so blue, red, and green. And we require the theory to be invariant under unitary transformations of this color index. So this is a unitary matrix, let's say with unit determinant. So these transformations form a group, SUN. So to make this invariance of the Lagrangian, if you write it down, if you write down it in the Lagrangian, it will not be invariant because the derivatives will also act on this matrix. So we need to add a compensating field. So the compensating field will then also be a matrix. So if there are n colors, this will be n by n Hermitian traceless matrix. And one can write down an analog of F mu for it. The Lagrangian will look absolutely the same. So this construction, simple as it is, describes all possible interactions in nature. So it turns out that strong interactions at the fundamental level are described by SU3 gauge theory, which is called QCD, quantum chromodynamics. So it's dynamics of colors. And the dynamical constituents of this theory are quarks, which carry color. And the gauge fields correspond to particles called gluons. Now, this is one example of the theories where perturbation theory doesn't give us the full truth. So it can be applied only at very, very high energies. At low energies, the perturbation theory would give us a wrong physical picture, because we know that there are no free gluons, and quarks can only appear as bound states inside protons and neutrons. So to describe this using from the Lagrangian is a challenge. This is still an unsolved problem. Just because the interaction strength is very strong, we cannot do perturbation theory. And non-perturbative methods in field theory are hard to develop. So weak interactions are described by SU2 cross U1 theory. So UN means that we don't impose this condition. So S means that we impose the condition that the determinant is equal to 1. So U1 means that U1 theory is the gauge transformations are numbers. So this is so Q in this terminology, QED is a U1 gauge theory. So weak interactions are actually described by a product of, there are two types of particles that mediate the weak interaction forces. And so, well, why don't we see these particles and, why there are no long-range forces associated to them? Well, the reason is that this symmetry is broken. And I heard that in the parallel course you studied broken symmetries, right? So this happens not only in condensed matter theory. So stuff gets broken even in particle physics. And what happens is that the part of this symmetry is not seen, and this is broken down to U1, which is just QED. So due to the breaking of the symmetry, the carriers of this interaction, which are called W and Z bosons, are actually very, very heavy particles. So their masses are in the range, well, they are 90 something GeV, so they're 100 times heavier than the proton. So this is precisely the energy at which the naive, or I mean, naive, but the simple Fermi theory of weak interactions becomes inadequate by power counting analysis. So the reason for that is that at these energies, the breaking of the symmetry is not important, and the correct description is in terms of well, the gauge interactions mediated by W and Z. So this is a picture of fundamental interactions as we know them, and it is based on gauge theory. So this is a very important ingredient in particle physics, and I guess you'll learn them in the next part of this course. So I stop here, and yes, you have some questions? Yes. That's an interesting question. Just a priori, one would think that quantization cannot change anything, right? So what means conservation of, what are the consequences of, say, conservation of electric current? This means that charge is not produced and does not disappear anywhere. So if you have some amount of charge, like charge 10, then it will not change with time. Now suppose that you, say, in a theory of electrons and positrons, suppose that you quantize this theory. Well, quantization cannot possibly affect this, right? It will still, I mean, the number of positrons and electrons cannot, I mean, they can only appear and disappear in pairs. So charge conservation carries on into quantum theory. Now, there are examples in which this is not true. So it is difficult to imagine how that can happen. And this has to do with infinities that appear in Feynman diagrams. So it turns out that certain symmetries get quantum anomalies. So naively, when you quantize, you may think that there is a conserved charge associated to them, but then there are quantum corrections that violate this conservation. Yeah. Yes?
Why don't we do it in
Can you maybe repeat the question?
I mean, say in the scalar field here.
Yes.
We draw the Feynman diagram, and then we count all the possible Feynman diagrams there. The symmetry case, and we got some factor there.
Oh, I see. I see. Why there are no symmetry factors in the? Yeah. So the reason is that all particles are distinguishable. So in QED, so their positron is different from electron and different from the photon.
Yeah, that's the thing when we consider
but,
the electron-electron scattering. So we can change the two electrons.
But I think, oh, let me see. So I'm afraid to give a wrong answer, but I think that in diagrams that involve only photons, you can have symmetry factors. But I'm not very sure. Yes?
Then you have one electron in the up, one electron in the down, we can change it.
Well, but there's a diagram that takes care of this. So there's a diagram that with two ends going parallel and then with two ends crossing.
Yeah, I don't say the crossing case, I say the parallel. We can change it to the system of the two electrons.
Not really. You're talking about this.
Yeah.
Well, these external lines have labels.
Yeah.
So this corresponds to certain momenta. So we can distinguish them. And so this diagram doesn't have any symmetries. Because you cannot interchange these two lines, right? Because this line starts with momentum p and this with momentum prime, and they're different. So there is no symmetry factor here. Maybe in some more complicated diagrams there are symmetry factors, but not in this simplest one. Yes.
Would you mind explaining why how you tell if you respond to the integral? Actually, I heard it's respond to the integral photon, and
well, this is because we can compute the angular momentum of this particle from the Noether's theorem, starting with the conserved current. Then we compute, and we see that this particle only carries orbital angular momentum, so there's no spin. I think I should defer all questions to. I'll be around, so if you want to ask something, just come back and ask. And I wish to thank you all of you for participating in this course, and have a nice day for the rest of the year. Thank you.